Okay, this is 8-channel scope here. Today's video is on the fuel pump circuit and how resistance affects the fuel pump circuit. So right here is our schematic. So as usual, I want you to freeze the video and take a picture, a snapshot of this circuit, and whichever feasible for you, take a snapshot, print it, take a screenshot, send it to another computer, possibly use your cell phone, take a snapshot of it and turn your cell phone horizontal and prop it up next to the computer that you're going to watch the rest of the video on. So anyway, okay, I hope you took your snapshot. It will make it easier to understand the rest of the video. And here we go. We're going to talk about this circuit. This is the fuel pump circuit on the 2004 Honda Accord. In the upper left of the video, as you can see, is the fuel pump relay. Honda refers to as PGI main relay 2. When it latches closed, it sends power to the fuel pump and it runs the fuel pump at full speed. This is not a multi-speed pump. It does not have any PCM speed control of it. Basically what you see in the illustration is a fuel rail with the 4 injectors above it. You see a pressure transducer on the rail, and you see the circuit going from the fuel pump relay, the latch part of the relay. The PCM has control of the relay. The latch part of the relay goes to the fuel pump. And on the way from the relay to the pump, you see 2 connectors. On the top connector, you see that green icon. That is resistance that we're going to insert into the circuit to see the way resistance affects a circuit. So basically, the transducer right here, as you can see, that is a 100 PSI transducer from eBay. You can get the parts online pretty quick and cheap. There's the 5-volt regulator. There's a 9-volt battery which powers it up, and it is custom probed to the Pico channel, the Pico scope, the 8-channel Pico. So now we're going to go to the scope and we're going to watch each channel. Okay. Okay, let's see if we can get this going. Okay. Okay, there's our scope, and I want to talk about each as you look at your schematic now, and I'll take one channel at a time. We'll discuss it and see what we're looking at. The blue channel is power feed to the fuel pump, which looks good. We're at charging voltage about 13.7, and look at your spot on the schematic, which makes sense. The red channel is also charging voltage. That's more downstream up at the fuel pump connector near the gas tank. The third channel, the green channel, is the transducer. That's showing our fuel pressure, which right now running is about 52 and change on this Honda. The fourth channel is we are tapped into the downstream oxygen sensor. There's a 0 to 1 zirconia sensor that being post catalyst, we will see the effect of fuel pressure, of course, on fuel mixture, and hence we will see where that voltage goes on that downstream O2 sensor. The fifth channel is we are current ramping the fuel pump. We're seeing how much amperage is flowing through the pump, and we can see the effect of resistance on the fuel pump when current is flowing. So anyway, you see what we're going across the screen. I'm going to stop the scope capture, and I'm going to stop the car, and we're going to discuss what we're looking at. Okay, as we can see, each channel, the top channel is voltage available outside the fuel pump relay. Looks like we're running about 14 volts, which is charging voltage. Makes sense. The red channel is also voltage at the fuel pump, which is about 13.57. Got a slight amount of voltage drop on the way to the pump. The third channel is the O2 sensor, which is the downstream oxygen sensor, which we're about, I'm going to say 585 millivolts. That one shouldn't be fluctuating too rapidly. In this case, it may be the catalytic converter was somewhat old, but anyway, that's it's still alive and it's responsive because I changed it a little while ago. The fifth channel is the current flowing to the fuel pump, and as we can see, we're about 5.4 amps. And as we zoom in on that, we will see a more granulated depiction of a fuel pump. Okay, right there is that is a current. So that's a fuel pump waveform. That's a current ramping the pump. We don't see any major dropouts that would depict the burnt spot on the commutator. I'm going to say there's 8 or 10 spots on the commutator. So basically, 8 peaks or 8 to 10 peaks or valleys would depict 1 RPM. Of the fuel pump. Later in the video, we'll talk about speed and pressure and stuff like that. But as I'll get back to normal, and I'm going to do what I'm going to go into the car, and I'm going to start the engine, and we're going to look at the waveform. As we're looking at the waveform, let me get the car started. Okay, now we're running. We got our voltages at the fuel pump. We got full voltage on blue and red. We got about 5.5 amps flowing to it. We got about 52 psi, and our O2 sensor is about the mid-range. If you look at your schematic now, look at the little green icon to the right of the connector on the circuit. We're going to engage and put resistance into that circuit and see the effect of resistance on pretty much every channel we have on this scope. So I'm going to go into the car, and you're going to just watch the scope, and you're going to see the effect of resistance, and we're going to talk about it. We'll replay it. Okay. Let's see now. Let's stop the scope and stop the car and play it back. See what we got. Okay. As you take a look at your schematics, you know what we look like as far as the effect of resistance. So in resistance, we're looking at a good screen now. Everything's normal, voltage is high. When that resistance enters that connector, let's see what happens. Okay, right there we see something. Right here we see something. We can see that our blue channel still remains strong. Now the reason that is because that is before our resistance. We're still at charging voltage there. But what happens to the red channel? The red channel is going to take a dive because when resistance gets into the circuit, it drops the voltage. So we're down to 7 volts at that fuel pump. And we can see that right there. Okay, now we're looking at, okay, let's look at the current now. The current before the resistance is there is about 5.7 amps. After the resistance enters into the connector, we're about 3 and change. So we've lost about 2 amps at the pump. And take a look at our fuel pressure. Look at that thing drop. We've gone from about 53 to about 35 psi. So you can see that resistance has a profound effect on it. Okay, now look what happens here is when the resistance goes away. You can see right here, our voltage is back strong. Our blue has always been strong. Our current went up. Our current was in about the 5 amp range, and our pressure just went up. It went from about 35 to about 50. You can see that quick rise when that resistance went out of the circuit, and our fuel pressure went back to normal. The O2 sensor is a little bit on the not as obvious right there. Okay, yeah, O2 sensor. I'm going to change the resolution. I'd like to get that to 1 volt. So we can kind of really see that. That's going to hog the screen a little, but nonetheless, once I filter it, we'll see that effect on resistance. So I'm going to start the car up, and we're going to see that again, and we'll kind of concentrate on the O2 sensor. We'll kind of take one component at a time to see the effect of resistance, of fuel pressure on that component. So I'm going to start the car again. Okay, the yellow is the rear O2 sensor. I'm going to watch about the effect of resistance on that O2 sensor. I will stop the scope. Stop the car. And let's look at the signals. Let's roll it back. Okay, so as we go, you can see the effect. Here's where we started the car. Okay, let's filter that yellow channel, kind of make it a little clearer. Okay, see, now you can see that channel a lot better because it's been filtered. Okay, here we go, driving along. Okay, now we got some action here. Right around here, we can see where the resistance came into the circuit. Those green crusties got into that connector, and we can see a profound drop in voltage. We also see a drop in pressure. We also see our O2 sensor the rear O2 sensor going down because it's getting leaner. That's the effect of low fuel pressure. It's going to make the mixture leaner. So we can see that. We can see our pressure is diving along with the O2 sensor. So they both respond to the situation of lower fuel pressure due to the resistance in the circuit. So here we go. Let's go a little bit more. Okay, here we can see again, now the resistance went away. This is a classic intermittent problem. This would makes a scope a really powerful tool because you could watch this over a long period of time. Okay, our voltage goes back up and our pressure goes back up and our O2 sensor goes back up. You can see that they all kind of respond to the normal fuel pressure due to the resistance, going away from the circuit. This is a classic example of a real intermittent problem in a connector that would, they may throw parts of the car and they may change the relay, they may change the pump, they may change the filter, certain things. But this would really be, this is really proves the power of a scope. So let's take another, now we're back to normal. Okay, now we have another drop. This is where resistance got into the circuit. Just as, red goes down, yellow goes down, and green goes down, green being fuel pressure, yellow being the rear O2 sensor voltage, and purple being the current flowing through the to the fuel pump. Okay, right now we got a little bit intermittent there. You can see it. You can see the effect. You can see how everything's tied together. You can see right here, when resistance gets into the circuit, right, what happens is the current goes down, the pressure starts to wane off, and that's the effect of resistance in a circuit. So basically, one thing more I want to talk about before I end this video is fuel pump speed, and that's a scope is a very powerful tool to determine that. So let's take the fuel pump speed at two different situations. This is when the resistance is not in the circuit. So I'm going to key in on here, and I want to get a good. Okay, let me stretch this, and I'm going to determine the fuel pump speed by, let's see if I can get this back. Come on. Here we go. All right. Okay. All right. Okay. That's our fuel pump, and we're going to count. I'm going to make the deduction. Either way, that this fuel pump has 8 bars on the commutator. If it has 10 bars on the commutator, either way, we're going to determine RPM, and we're going to determine the effective resistance on RPM. So right here is my signature. We're going to call that my signature notch, and I'm going to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm going to roll the measurement from here to here, and I'm going to count. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, let me get that back. Okay, I'm going to go back to here. Okay, let me go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so right here would be one pump rotation. Let me see about that. See, this is the tricky part about fuel pumps. You got to find that anomaly, that kind of signature notch. And this one is, hey, maybe it's an 8-bar pump. Okay, 1, 2, 3, 4, 5, 6, 7. Okay, I'm saying this is an 8-bar pump. Okay, see that? You can see the little bit of a lower pull on that commutator bar. Maybe the sign of some wear, but nonetheless, it's not. We don't see a pure dropout like an open spot. That would cause like an intermittent no start, or something if you bang on the tank and the pump starts working again, one of those deals. Nonetheless, we have 7.401 milliseconds per rotation. So I'm going to go to my cell phone, and you can do this. We want to divide 60,000 by 7.4 because that'll give us the RPM. The reason I picked 60,000 is because I'm trying to determine revolutions per minute. And in 60,000, in 1 second is 1,000 milliseconds. And and there are 60 seconds in a minute. So let me go to my phone, if I can find it. Okay. Go to the calculator. And you could do this on your phone or any calculator device. Calculator. Okay. Calculator. Okay, so 60,000, 60,000 divided by 7.4. 7.4 equals, that is 8,108 RPM. Okay, not that I don't know if you can see that. I'll just tell you, you'll believe me, it's 8,100 RPM. So now we're gonna go to the spot where the resistance entered the equation. Let's get back to the regular screen, and let's move over to where we know things change, right here, okay? This is where the resistance entered the equation. Our fuel pressure dropped, our current dropped, and we know right here, we're gonna look for the RPM of that pump. Okay, let me stretch it. Let me get some vertical zoom. Okay, so I'm gonna take the cursors. All right, let's see this. Let me get that again. Okay. Okay, so let's take a count now. We'll go right here, and then we'll go 8 bars over to there. So we got 1, 2, 3, 4, 5, 6, 7, 8. Okay, now we're looking at 13.73 milliseconds. So we'll divide 60,000. Let's clear the calculator. 60,000. Okay. 60,000 divided by 13.73 equals, okay, that is 4,369 revolutions per minute. That's a lot slower. Now you see the effect of resistance has on fuel pump speed and hence fuel pump pressure. So basically, the gist of this video is to show you the effect of resistance on a fuel pump circuit, where this would be really tough to find without a scope. In this case, we had pressure transducer, we had the O2 sensor monitored to see where the mixture went, and we had voltage available coming out of the fuel pump relay and at the fuel pump. So we would deduce that the resistance is somewhere between the fuel pump relay and the fuel pump. Thank you very much for watching this video. I plan on making more. They'll only get better, I hope. And all the best to you out there. Thank you.